Hey Raiders, we're going to take a look at a level 3 cliff problem here together. And just a general note, remember that the more complex a scenario is, like this, the greater variety of ways it can be solved. So I'm only going to show you kind of one specific approach here, but in another video or screencast, I might touch on some of the other ways you can analyze this problem as well. So in this scenario, we've got a ball launched 15 meters per second at a 40-degree angle from the top of an 80-meter cliff. And the base questions that I typically ask here: how much time does it take for the ball to hit the peak? What's the ball's maximum height above the water? How much time does it take for the ball to hit the water? And what's the ball's velocity at 1.8 seconds? So the first thing we need to do, because velocity is a vector quantity, and as velocity is launched at an angle, or it's not completely in the x direction or completely in the y direction, we're going to need to use our basic trigonometry skills to break this up into its x and y components, because you can't take this angled velocity and put it in an equation with gravity that's completely in the y direction, or you couldn't put this 15 meter per second angular velocity in an equation if you're analyzing a horizontal motion, like you wanted to know the ball's range, you know, how far from the base of the cliff it was when it hit the water. So we'll do that first. So remember that we use SOHCAHTOA as just a little reminder for ourselves about the three basic trig functions of sine, cosine, and tangent, and what combination of side lengths we set up ratios for. So we'll take that angled 15 meter per second velocity and set up a right triangle here, where the horizontal component, as this thing goes up and to the right, the horizontal component going to the right, we'll call it Vx. And then the vertical component that initially goes up before gravity ultimately pulls the ball down will be Vy. And this is a 40-degree angle. So relative to this 40-degree angle, the opposite side to that angle is right here. And the side right next to the 40-degree angle, that's adjacent. And then the overall velocity is the hypotenuse. So identifying all three sides of this triangle, the hypotenuse and the two legs, that's important to be able to figure out which trig function you're going to use. So it doesn't matter if we get the x or y component first, so let's get the x component first. Well, relative to the 40-degree angle, Vx, the horizontal component, is adjacent to the angle, and we know the hypotenuse. Well, looking at SOHCAHTOA, that specific combination is cosine, the adjacent side length divided by the hypotenuse. So cosine of 40 degrees equals Vx over 15. So this is an algebra problem now. We want to get Vx all by itself, and right now it's being divided by 15, so we have to undo that. So the opposite or inverse operation of dividing by 15, multiply by 15. And we'll multiply both sides of the equation by 15. So now the velocity in the x direction, the horizontal component of the velocity, is going to be 15 times the cosine of 40 degrees. So you can type that into the calculator just like you see it, and you don't need to hit the multiplication or anything like that. 15 cosine of 40 degrees, and you get about 11.49. So that means the horizontal component of the velocity is about 11.49 meters per second. So if you're doing anything where you're going to analyze the horizontal motion of the ball, the velocity you're going to use is not going to be the overall velocity of 15, it's going to be 11.49 meters per second, because that's how fast the ball is going horizontally the entire time it's in the air. So that's a constant velocity. And it's constant in the x direction because the only thing acting on the ball when it's in the air is gravity, which impacts the y direction. So now, having said that, let's get Vy, the y component of the velocity. Well, relative to the 40-degree angle, this is the opposite side, and we know the hypotenuse. So if we look at SOHCAHTOA, that combination of opposite and hypotenuse sets up for sine. So sine of 40 degrees equals Vy over 15. So multiply both sides by 15. So Vy is going to be approximately equal to whatever 15 times the sine of 40 degrees is. So you can type that into the calculator just like you see it. 15 times the sine of 40 degrees. So it's about 9.64, and this is velocity, so it's meters per second. And before we move on, let's just stop and take a look at these components relative to each other. The ball was launched at a 40-degree angle, which means it's a little closer to horizontal than vertical, and sure enough, the horizontal component is a little bit bigger than the vertical component. All right, so moving on. So I said there's multiple ways you can analyze this problem. But in this video, we're only going to focus on one technique. We're going to use the QuadTIC program, the quadratic formula program on the calculator. And if you remember, we've talked about this in class. Not only when we set it up will it tell us the time for the ball to hit the water, meaning analyzing the entire trip, it'll also give us the answers for A and B as well. And we'll talk about in a Screencastify video how you can use Desmos to do the same thing. So technically, we're only directly setting up to analyze part C here, but coincidentally from the QuadTIC program, we'll also get the answers to A and B, details about the ball when it's at its peak. So we're going to analyze, if we wanted to find the time for the ball to hit the water, well, in order to figure out the time to hit the water, that's not just analyzing up to the peak, that's whole trip. So we're going to analyze the Y direction, whole trip. Remember, you got to tell me, with any calculation you're doing, tell me what segment of the problem you're analyzing and tell me what direction you're analyzing. So given information, the initial velocity, it's not the overall 15 meters per second because that's not in the Y direction. Remember, these are all vector quantities, direction matters. So the initial velocity is what we calculated earlier. It's about 9.64 meters per second. And since we're analyzing the Y direction, gravity plays a role here. That will accelerate the ball downward at 9.8 meters per second squared, so negative 9.8 meters per second squared. And for the whole trip, displacement is negative 80 meters. Remember, displacement describes where something ends up compared to where it started. So a common mistake here is to just put 80 meters because the cliff is 80 meters high. But the ball ends up 80 meters below where it started, so displacement's negative 80 meters. And we're trying to find time. So again, the way we're setting this up, we're directly analyzing time for the ball to hit the water. But again, from the QuadTIC program that you'll have access to in the graphing calculators in class, it'll also give us information about when the ball's at its peak, so that'll also answer A and B as we go along here. So if you look, this specific combination of variables sets up for using D equals VIT plus 1/2 AT squared. So now just substitute your values in. Negative 80 is approximately equal to 9.64 T plus 1/2 times negative 9.8 T squared. So we can clean this up a little bit right here. So we're going to have negative 80 is approximately equal to 9.64 T. I realize I just forgot that right there. Minus 4.9 T squared, because 1/2 of negative 9.8 is negative 4.9. So now if you look here, we're trying to find time, but because we have a term with T and with T squared, you're not going to be able to isolate T all by itself to get T equals and then be able to solve it. So here's where the quadratic formula kicks in. And remember, we've talked about this, the quadratic formula. If you take your equation and you put it in standard form, of ax squared plus bx plus c equals 0, then that would enable you to be able to use the quadratic formula of negative b plus or minus radical b squared minus 4ac all over 2a. And you could methodically go through and do your substitution to figure out what values of time would make this equation true to be able to answer how much time it takes the ball to hit the water. But we can use the QuadTIC program to do this more easily. And so if you look at our D equals VIT plus 1/2 AT squared equation, it does not equal 0 right now. It equals negative 80. So we put it in standard form. We got to make it equal 0. So add 80 to both sides. So now 0 is approximately equal to 9.64 T minus 4.9 T squared plus 80. So we're a little closer to having this in standard form, but notice here, has to be ax squared, so it's the squared term. So it's going to be negative 4.9 T squared plus 9.64 T plus 80 is approximately equal to 0. So here's your A term, here's your B term, and here's your C term. So just one little clarification here. Don't confuse the A of the standard form of ax squared plus bx plus c equals 0 with A for acceleration. So now at this point, you could, kind of systematically substitute your values in, say negative 9.64 plus radical 9.64 squared minus 4 times blah, 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 blah. You can keep going that way, but the QuadTIC program can do that more easily. So let's pull that up. So PRGM program. quad tick. So now your A value doesn't mean A for acceleration, it means from the standard form. So it's gonna be negative, and you have to use the negative sign, not the minus. Negative 4.9, hit enter. Then B value was 9.64, and the C value is 80. So if you look, it gives you two possible times that will make this equation true. Now, even though negative 3.17 is a valid mathematical solution to this equation, we can't have negative time. So we know that means it's going to take the ball about 5.14 seconds to hit the ground. And that's for part C. And in terms of documenting work, you can just kind of write something on here like quad tick, ... That's your way of communicating to me. All right, Mr. Dubois, this is the equation I put into the quad tick program, and you got time here. Now, we talked about the fact that in this problem here, we're directly setting up to analyze part C, time for the ball to hit the water. We've got that answer now, about 5.14 seconds. But I also said that the quad tick program will sort of coincidentally also give you the details about the ball when it's at its peak. So that would be parts A and B. So all you've got to do is when you're on the quad tick screen here and you got time, just hit enter, it'll bring you to the next screen, and you see it'll give you the X and Y coordinates of the vertex for the parabola that is represented by this equation. And if you think about this, the X coordinate, if you look at the equation here, the independent variable t, time, that's the X coordinate, and then the dependent variable displacement, the ball's displacement, which depends on how much time it's been in the air, that's the Y coordinate. So when you see X of the vertex and Y of the vertex, when you see X of the vertex is about 0.98, well, X is really representative of time, so that means it's going to take the ball about 0.98 seconds to hit the peak. And the Y of the vertex, that's the dependent variable that depends on how much time it's been in the air, that means the maximum height above the water, which is the answer to part C, is about 84.7 meters. So you can just document that on your paper by saying X of vertex, and then just tell me that you know what this means, so you can just kind of say like time to peak. That's your way of communicating to me that you recognize that's what it is. And in this case, it was about 0.98 seconds. And that's the answer to part A. And then the Y of the vertex, again, let me know that you know what this means. That's the maximum height, and that's approximately 84.7 meters. And that's the answer to part B. It's the maximum height above the water. So now there are other ways that you can do this, and you can do this using Desmos, because just really quickly, if you sketch this, if you use Desmos and you graph the parabola, you'd end up with something that looks like this. And this 0 over here would have coordinates of about 5.14, 0. And then the vertex, the high point of the graph, that corresponds with the X and Y coordinates of the vertex. So if you look this up in Desmos, you would see that at about 0.98 seconds, the ball reaches its maximum height above the water of about 84.7 meters. And if you just stop and think about the fact that it takes the ball almost a second to go up to the peak, let's see if that kind of makes sense here. Well, if you look at your Y component that we figured out initially, it was about 9.64 meters per second. And on the way up, we know that gravity's slowing the ball down, and it slows it down at a rate of 9.8 meters per second every single second. So sure enough, if the ball's initial upward velocity is less than 9.8, but it's almost 9.8, it should take it almost a second before it reaches its peak. So that kind of checks out. Okay, and then the last part of this here, the ball's velocity at 1.8 seconds. So what we need to do here is, just like when we started the problem, at the initial time 0, when the ball was launched, it had a horizontal and vertical component to its velocity. Well, later on in the trajectory at 1.8 seconds, which we now know the ball's on the way down because it only took 0.98 seconds to get to the peak. Well, at 1.8 seconds, the ball's going to be on the way down. So it's also going to have a downward Y component to its velocity and a horizontal X component. And if we can find those components, then we can use some Pythagorean theorem skills and some inverse trigonometry to answer the question, what's the ball's velocity at 1.8 seconds? Because since you're looking for velocity, it's a vector quantity, you need magnitude and direction. So let's set that up here. Let's kind of make a little snapshot about what's happening to the ball at that critical time of 1.8 seconds. So I'm going to label this velocity at 1.8 seconds. Well, we already know what the ball's velocity is in the x direction, because the entire time the ball's in the air, the only thing acting on is gravity, which has no effect on the y direction. So that x component of about 11.49 meters per second, that's going to be constant the whole time. So we already know the ball's horizontal component at 1.8 seconds, 11.49 meters per second. Now, we knew the ball's initial velocity in the y direction of 9.64 meters per second, but that was only at the initial launch. Because of gravity, that's changing every instant. So now we need to do another calculation. We need to analyze the y direction to figure out the ball's velocity at 1.8 seconds in the y direction. So we're going to set up to analyze the y direction. And it's not up to the peak, it's not whole trip, it's until t equals 1.8 seconds. So let's see what we know here. Our given information, we know the initial velocity is approximately 9.64 meters per second. We know it's going to accelerate downward because of gravity, so that's going to be negative 9.8 meters per second squared. And we know that because we're setting up to analyze this specific point in time is 1.8 seconds, and we want to find final velocity. It's not the ball's final velocity ever, but for this segment it is, which is what we want, the velocity at 1.8 seconds. So this is going to set up for using VF equals VI plus AT. So it's approximately equal to 9.64, the upward initial velocity, but then the entire 1.8 seconds that we're focusing on, it's accelerating down because of gravity. So this works out to be -8. So the final velocity is -8 meters per second in the y direction at 1.8 seconds. So the negative sign, remember velocity is a vector, so this negative sign tells us direction. So when I come over here with my little snapshot of what the ball is doing at 1.8 seconds, since the y component is negative, I'm going to draw it downward. And to try and keep it proportional to the length of the other vector, so I'll make it about 3/4 the length. So -8 meters per second. The negative sign is just there for direction. So now that I've drawn it downward, I'm actually not going to put the negative sign there. So we know that the ball is going down and to the right. And if you think back to how we had set up before, we knew the x and y components, and they were connected tip to tail to show the ball going up and to the right. Well, right now, these vectors are connected tail to tail. So I'm going to translate this vector over here. Now they're connected, the tip of the x vector is connected to the tail of the y vector. And sure enough, now when I close out this right triangle, v sub r, the resultant velocity, is pointing in the direction that's something that's going down and to the right. So if you notice here, we've created a right triangle. We know two side lengths, so we can use Pythagorean theorem. Leg 1 squared plus leg 2 squared equals hypotenuse squared. So 11.49 squared plus 8 squared equals resultant velocity squared. It's approximately here. This works out to be 196.02 is approximately equal to resultant velocity squared, but we don't want the resultant velocity squared, we want the resultant velocity. So take the square root of both sides. So the resultant velocity is approximately 14 meters per second. Now, that takes care of the speed. If the question just said how fast is the ball going, you'd be done. But the question said, what's the ball's velocity? So velocity is a vector quantity, we have to do direction. So now we're at the very end of this problem here. We want to get this unknown angle theta. It's a certain number of degrees below the horizontal. So we're going to do an inverse trig function here. So relative to this angle, this side is opposite, this side is adjacent. We're going back to SOHCAHTOA, sets up for tangent, because tangent is the ratio of the opposite side length to an angle divided by the adjacent side. So tangent of this unknown angle theta, it's going to be approximately equal to the opposite side length, 8, over the adjacent side of 11.49. So now we're going to do an inverse trig function. So theta is going to be tangent to -1 of this ratio. So on the calculator, we'll do second tangent, and then now you put the ratio that you're dealing with. 8 divided by 11.49. So it's about a 34.8 degree angle. So putting the whole answer together, the ball's velocity is 14 meters per second at 34.8 degrees. Now I got to be specific. It's not above the horizontal, like when the problem started, it's below the horizontal. All right, Raiders, hope this helped.